Attendees are in listen-only mode.
Well, good afternoon and welcome one and all to the Pacific Ocean Education Team's quarterly webinar. Today we are going to be featuring a guest speaker who talking about interglacial sea levels, as you can tell from the screen. My name is John Morris, and I'm an interpretive specialist here in the regional office in Alaska in Anchorage. And Jim Pfeifenberger isn't available this month. He was tied up in a teacher's workshop down in Seward. And so we have a guest moderator who will be joining us from down in California, Kate Faulkner. And I'll introduce her in just a second. First of all, let me just explain for those of you who are new to the webinar series, it's pretty straightforward. We have a number of attendees that join us, and you all join us in listen-only mode because if you're all open with microphones, the audio gets kind of crazy pretty fast. So what we would like, if you have comments or questions, if you're having trouble hearing us, just use the chat box there at the bottom of your control panel. It says questions or chat. Just type them in, and we'll be monitoring that, and we'll either answer you in that box or we'll bring it to everybody's attention should that occur. Also, if you have comments during the presentation or questions, you can use that chat box to do so, to ask them as well. The normal procedures are that we have a presentation that lasts about 45 minutes, and we'll follow that up with some time for questions and answers at the end. So you can ask questions anytime, unless it's germane to the actual moment in the presentation. We'll probably hold the question to the conclusion and do a Q&A session before we can complete it. Also, as Jim would remind you, we do record these sessions, and we'll be posting them on the archive site, which Jim maintains there at the Ocean Alaska Science and Learning Center, and we'll provide information about that after the fact in email if you would like. So with that, let me kind of introduce the kind of guest facilitator today, Kate Faulkner from Channel Islands. Take it away, Kate.
Okay, thank you, John. Yeah, I'm very excited to be participating today. As most of you know, these webinars are a regular series with various ocean stewardship education topics. So I just wanted to remind people that the next webinar is scheduled for November 15th, and the speaker and the topic is still to be announced, so be looking for that. So today we're very excited to have with us Dr. Daniel Muhs. And I've had the pleasure of working with Dan for a number of years, and so that's why I got the honor of being the person to introduce him. Dan is a research geologist with the U.S. Geological Survey, where he's worked since 1983. Primarily he's worked on geologic records of climate change. Dr. Muhs grew up in Santa Barbara County, not far from the Channel Islands where I work. His master's and bachelor's degrees were completed at the University of Illinois, and his PhD work was at the University of Colorado. And he studied the ages of marine terraces and the origin of soils on San Clemente Island for his PhD. Since that time, Dan's worked with USGS in Alaska, Hawaii, California, the desert Southwest, Rocky Mountains, Great Plains, Mississippi River Valley, and Florida. He's also done quite a bit of work in national park units and is a very dedicated person regarding the purposes and missions of national parks. Dan specifically has worked in Badlands National Park in South Dakota, Wrangell St. Elias in Alaska, Mojave National Preserve in California, and he's continuing to work with us here at Channel Islands National Park. Dan will be speaking on past interglacial sea levels, lessons for the future. Dan, take it away. We're looking forward to your presentation.
Well, thank you very much, Kate, and welcome to everyone. This is only the second webinar I've ever done in my life, and the first one was about 2 weeks ago and was my project proposal review. This is where they determine whether or not they're going to write you out a check for the next fiscal year for your project. So it was something of a trial by fire, but I managed to get through it. And I hope this one will be easier, and at least not talking about budgets today anyway. But at any rate, thanks again, Kate, for introducing me, and thanks, John. And it's a pleasure to be here. And it's appropriate that Kate is moderating this because a lot of examples that I'll use today are from her park, from Channel Islands National Park, where we have some of the best sea level records in the geologic past of any place in North America and indeed the world. So I'll talk today a little bit about past interglacial sea levels, and I have in the title here Lessons for the Future, because one of the primary reasons why we study past sea levels is to learn something about where we may be headed. And whoops, we've got our first glitch here. I'm trying to change slides and not succeeding.
It's happened before. Maybe try exiting out of the PowerPoint slideshow and going back in again.
All right, let's try that.
Often happens with us.
Okay.
There we go.
All right. Hopefully that's all on there, and hopefully everyone can see it. Here I've listed some of the issues with regard to sea level, and that is rising sea level at present has raised concerns about impacts on the world's coastlines, not only a lot of the world's population and its infrastructure, but also habitats of animals and the plants that occupy those areas. All of these things could be affected by rising sea level, and so we're talking about a significant portion of the world's population of plants, animals, and humans, and the environments they live in. A second issue related to this is how high can sea level get? This is a question we really don't know at this point. We don't know also how fast it can rise. And these are questions that are being asked in light of the present observation that sea level is rising right now. And our project attempts to answer these questions, as I say on this third item here, by study of high sea levels that are in the geologic record. When we can't see the future, but we're worried about a process going on in the present, the geologic record can often give us some insight as to what we might expect in the future by seeing what has occurred in the past. And the final bullet point that I've listed here is our approach to this, and we employ shoreline mapping, that is mapping of past shorelines. We look at the stratigraphy of the sediments associated with that. We measure their elevations. We get precise geochronology, or ages of those, using two methods here, one referred to as uranium series or U series, and then strontium isotope dating, U series for the younger ones, strontium isotope for the older ones, and then also paleozoogeography, or examining the fossil assemblages in these old shoreline deposits. Most of these are composed of extant species, and knowing something about their zoogeography, that can tell us something about what the water temperatures were like at the time of past high sea levels, whether temperatures are warmer or cooler or about the same, and that in turn can tell us something about currents as well as how high sea level was. Okay, I've learned what I have to do. I have to click my mouse to change slides. I can do that. So we are looking primarily at records over the glacial and interglacial cycles of the past 2.5 million years or so. This constitutes a period of time that in geology we refer to as the Quaternary period. You may have heard the term Pleistocene. That is most of the Quaternary. Another term you may have heard for this is simply the Ice Ages. But interspersed between Ice Ages, we also had relatively warm periods that we refer to as interglacials. And these two maps of North America that you see show what the changing geography of North America would have been during the last glacial period, and that was about 25,000 to 10,000 years ago. You'll see a shorthand we use in geology here. Ka stands for kilo-no, or thousands of years. So the last glacial period was about 25,000 years ago till about 10,000 years ago. And on this map on the left, you can see what it looked like. A couple of big ice sheets on North America, the Laurentide ice sheet over most of North America, the Cordilleran ice sheet over in the western part, and then greatly expanded ice caps on many of the world's the continent's mountain ranges, such as in Alaska, and an expanded Greenland ice sheet as well. And then over on the right-hand panel, you can see what things look like during the present interglacial period, which has been about the last 10,000 years. Greenland has shrunk back to a lesser extent than what it had during the last glacial period. All that's left of the Laurentide ice sheet is that little teeny ice cap called the Barnes ice cap on Baffin Island in Canada, just south of Greenland, and it's actually going fast as well. It's melting very rapidly now, and we're seeing a lot of melting in Greenland at the present time too. But in any case, these will give you some ideas of what the contrasting nature of climates were like during the glacial-interglacial cycles of the Quaternary period, the last 2.5 million years. And a lot of our focus is on interglacials like the present one, but we're particularly interested in interglacials that may have been warmer than the present that could be analogs for what we might be headed for in the future. So we may see even less of Greenland, for example, than at the present time. Why does sea level rise and fall over glacial-interglacial cycles? This is primarily a simple mass balance between the growth of ice sheets on the continents, and I've diagrammed that over here on the left. I'm thinking that, if I recall correctly, that you can see my mouse as a pointer. Here we have an example of an ice sheet on a continent, and that has formed by snow that has fallen on the continent and has persisted as snow through many, many summer times and up to the point where it builds up glacial ice. And most of the world's moisture comes from the world's oceans, so air masses that are passing over moisture sources like the oceans experience evaporation, moisture into the atmosphere that's transferred laterally to continents, falls as snow, builds up glacial ice, and then sea level will lower. Well, as ice sheets like this melt and return water back to the ocean, sea level then, of course, will rise, just the reverse of this. So it's a simple kind of hydrologic cycle, but in this case, including the cryosphere as well as the atmosphere and hydrosphere in this sort of a cycle through time. So we've seen a succession of at least 25 of these cycles, actually more than that, over the last 2.5 million years. And what we're particularly interested in are those periods where we had conditions similar today or warmer than today during interglacials. And one of the most remarkable accomplishments of the 1950s and studied by a lot of oceanographers and marine sedimentologists and paleontologists is the discovery that these glacial-interglacial cycles are tracked in the oxygen isotope composition of foraminifera, or these microorganisms that occur in the oceans. They respond to let me put it another way, the oxygen isotope composition, oxygen 18 versus 16 in foraminifera, which is in their shells, is a function of two things, water temperature, which is colder during glacial periods, and also the composition of seawater in terms of oxygen isotopes, which changes between glacial and interglacial periods. I won't go into all the details of that. We can if you like during the question and answer period. But the point is these actually both act in the same direction. So when we analyze the oxygen isotope composition of foraminifera shells in deep sea cores, we can track glacial-interglacial periods. And this curve, shown in yellow here, shows you an example of how this takes place and how it has occurred over the last 400,000 years. So this is a time scale, the horizontal here, in kiloannos, or thousands of years, starting here with the present, going back 100,000 years, 200, 300, 400, and so on. And where we have peaks on these curves, we're in the major parts of our interglacials, the last interglacial being this big peak that you see here, present interglacial being right here. The last glacial period is down here. And so this is essentially an ice volume curve and temperature curve. And because it's an ice volume curve, in part, it's also partly a sea level curve. So we have sea levels that are relatively high here, here, and here, here, and then our low points here are times when sea level was low during our glacial periods, the last glacial being this period right in through here. The problem is that because this is both a temperature record and an ice volume record, we can't really sort out exactly what sea level was from this kind of a record, even though in theory it's possible. But we can't always decouple the temperature effect and the ice volume effect. So it's not exactly a sea level curve. It partly reflects sea level, but not completely. So that is part of the reason why we study fossil shoreline deposits, because they're direct records of high sea levels on the land, and will give us a more exact picture of how high sea levels might have gotten during our interglacial periods. So in theory, this is a more continuous, complete record, but it's not a direct record, or not a unique record of sea level. It's also got ice volume in there as well. But it's a useful thing to compare to, and it certainly shows you the nature of the record. And we're particularly interested, like I say, in these past periods when sea level or temperatures in the world as a whole might have been as warm or warmer than it is at present. So what I've done in this next diagram is show kind of a translation from that sort of a record. This curve that you see over here on the right in blue is an oxygen isotope curve, exact same one that we saw in the last slide. And what I've done is translate that to a coastline that you see over here on the left, where we've got a stair-step series of coral reefs that have been uplifted. This is an example of the kind of record we see on an uplifting coast of the sort we see, for example, at Channel Islands National Park in California. We don't have coral reefs there, but we have wave-cut benches that contain little solitary corals. And corals are important, actually, because that is the one organism that we can use to date some of the younger high sea stands using uranium series. Only organism that takes up uranium from growth, or when it's growing, from seawater. But at any rate, you can see here, modern sea level is represented in this case by a coral reef right here, shown in pink. And then fossil coral reefs I've shown in purple. There's these little coral heads here. And you can see that this one, the first one up from the modern sea level, dates to the last major interglacial period. The next one up dates to the one before that, and so on back in time. And oxygen isotope stratigraphers number oxygen isotope stages or interglacials with odd numbers like this. 1, 3 is this little one right here, 5, 7, 9, 11, and so on. And then our glacial periods are even numbered stages, 2, 4, 6, 8, 10, and so on. And so we don't have our glacials periods, our oxygen isotope even numbered stages recorded on our coral reefs here. But we have our interglacial high sea stands recorded in these coral reefs. During low stands of sea, there would have been terraces like these, or coral reefs like this formed, but they'd be way offshore down here somewhere with a low sea level, and they wouldn't be visible to us now unless the area was undergoing a very, very high rate of uplift. Some places do have that, but most do not. So that's an example of the kind of record we see, just diagrammatically, on an uplifting coast of sea level record for the past 4 glacial interglacial cycles. In the real world, it looks like this. This is an example from California. This is from San Clemente Island, California. And here's an example of a wave-cut bench. This low one here dates to the last interglacial period, about 125,000 years old. This one dates to about 200,000, 300,000, 400,000, and so on. So there's a lot of these on this particular island. It's undergone a moderate but fairly steady rate of uplift. And so we have marine terraces like these, they're called marine terraces, that go back almost to 2 to 2.5 million years ago, about the time that the Quaternary period started. An example of a lower rate of uplift coast is this one from Channel Islands National Park. This is little Santa Barbara Island. It's only about a square mile in area, but it has records of about 5 interglacial high sea stands just in this 1 square mile. So it has a remarkable record of climate change over the last couple of million years just in its 1 square mile area. What you're seeing here are the 2 lowest terraces. This one at about 7 to 9 meters above sea level, this bench that you see right here. And it has both marine deposits that are shown in this kind of white color and some slope wash deposits from this cliff in this brown color here. And then above that on the skyline you can see another higher terrace. It's up around 50 meters. And the National Park Service campground and the headquarters for this particular island are located right on that 50-meter marine terrace. This is an example of an island that's undergone very, very little uplift over time compared to San Clemente Island, so we don't see as many terraces, and we don't have all the interglacials recorded here. And this is part of the nature of the geologic record. We always have gaps. We have parts of the record that are incomplete. Okay, if we move to an area where we don't have uplift, here's our oxygen isotope record again. This is the same curve that we've been seeing here. But let's move to a place where we have, say, no uplift going on at all, or possibly just some very slow subsidence where the maybe going the continent or coastline may be undergoing some slight falling over time, or maybe nothing at all, just staying right where it is. What we get in this case, and again I've used coral reefs as an example, these are little coral heads. The pink ones here are the modern coral reef, just below modern sea level. Well, what I've shown here is an example of a fossil coral reef that may be present a little bit higher than modern sea level, that records this last interglacial period, or marine isotope stage 5.5 here. Below that might be one that records isotope stage 7, or the previous interglacial period around 200,000 years ago. And that one you see is buried by the younger coral reef. And we can sometimes find a buried soil that marks where that was subaerially exposed and or soils formed and that sort of thing. So we can see a series of stacked marine deposits in a sequence like this on a lot of stable or slowly subsiding coastlines. A good example of this is the Florida Keys. This is an example from Key Largo, Florida. And what we're looking at here is 2 coral reefs. This one right here on the surface dates to the last interglacial period, about 125,000 years ago. And then this one down below and down into the water of this abandoned quarry and down below it is from the penultimate interglacial, about 200,000 years old. The contact between these two can be seen by this kind of a feature that looks like a horizontal fracture right in through there. And that's actually a contact, geologic contact, representing about 100,000 years of exposure between this interglacial high sea stand and this interglacial high sea stand. And this is a good example to show you then of how we can, from a stable coastline, get a good sense of what some of our past high sea levels might have been. You can see that the penultimate interglacial sea level has to have been higher than present because we're on a stable coastline where there's been no uplift, no subsiding, staying right where it is, and sea level was clearly higher because the reef is higher than sea level. The water level in this quarry is right about at sea level. And the last interglacial was even higher than that because it's stacked up on top of this one. And so we can get an estimate just by simple measurements of the elevation of the top of this surface, as to how high these 2 high sea stands were in the past. You can see already that the previous 2 high sea stands were higher than modern sea level is at the present time. So, as an introduction then, what are some of the key questions that are being answered or being asked? We hope to try to answer them, but certainly they're being asked. And a lot of these are things that have come up just in the last month or so in the Intergovernmental Panel on Climate Change, which has a report which is currently in progress. And I was a part of the past sea level group that was trying to assess what we know and what we don't know about this kind of thing. And 3 questions that have come up that we'll explore a little bit today are these. the timing of past interglacial sea level high stands, marine paleo temperatures during those high sea stands. In other words, how warm were the waters during that time? Were they warmer than present, colder, or about the same? And then magnitudes of past high interglacial sea stands that I've already given you an introduction to with this example from the Florida Keys. So in places like California where we're undergoing uplift, we can't answer this question about magnitudes because we know that there's an element of uplift or tectonic rising that is going on that complicates that. But we can answer questions about marine paleo temperatures, and we can certainly answer questions about the timing of past interglacial sea levels. So when we want to work on magnitudes of past interglacials, we move to places that are tectonically stable, like the Florida Keys, parts of Hawaii, and so on. So, example 1, when was the last interglacial, and how long did it last? And here's some examples from some of the places we've worked. Since this is a Pacific group, I've tried to pull some examples from parts of the Pacific here. One of the best ones is from the island of Oahu. It's not a very pleasant place to work, but you got to do some of this stuff once in a while. So we put up with working on Hawaii for as long as we could, and which turns out to be not nearly as long as we'd hoped. But what you can see here is the island of Oahu is rimmed as these turquoise or light blue lines. This is the last interglacial shoreline, which is referred to as the Waimanalo shoreline or Waimanalo limestone because it's a coral reef, and much of the city of Honolulu is built on that rock itself. And from a variety of places where we've collected corals for dating, such as these that you see over here, we've got the range of ages that you can see that we've obtained by this, and they range from about somewhere in the 120,000 year range, one place a little bit older, down to about perhaps as young as 113,000 in some places, a little older in a few other places. But this indicates a high sea level that lasted at least 12,000 years and possibly as much as 21,000 years. And this was a good lesson for us that interglacial periods can be quite long. It used to be thought that the last interglacial period, based on the oxygen isotope record, was perhaps only about 4,000 or 5,000 years long. We now know it was much longer than that, and therefore the present interglacial could be many millennia away from ending if the past is any indication. And this is all totally independent of anything to do with carbon dioxide or global warming, but just on the basis of past climatic conditions, interglacials can be quite long. And Hawaii is a good example of that. We have good examples also from California, from the Channel Islands and elsewhere. And here are some numbers that look very similar. From San Nicolas Island, 121 to 116,000. Palos Verdes Hills near Los Angeles, a little bit wider range. San Clemente Island, also about the same. San Miguel Island, the Channel Islands National Park, 121 to 114,000 years old. And Isla Guadalupe. These are all coming about the same. They show, in this case, a little bit shorter interglacial, one that probably lasted at least 9,000 years. But here we expect to have a shorter record. This is an example of a different kind of geologic record. These are wave-cut benches. So the first part of an interglacial period is occupied primarily by the erosive work of cutting those marine terrace benches. And what we're dating are the shells and corals that are left behind during the latter part of an interglacial period, whereas a coral reef that can keep up with a rising sea level is going to record the very earliest part of an interglacial. So just on geologic principles, we expect to see about the same ending time for perhaps both of these when sea level starts to drop, but different beginning times in places like Hawaii versus places like California. And we see that here when we move to places like the Caribbean, like the Florida Keys, the Bahamas, and so on. Now we're starting to see a few older ages, 136,000 from Barbados, 126,000 from Curaçao, Puerto Rico, 127,000, Bahamas, 130,000. We're starting to see with the coral reef record again an earlier beginning because we've got reefs here that can keep up with a rising sea level unlike the sort of record we see in California. But the ending times are coming in about the same. A lot of 113,000s in our record and so on. But again, a best estimate here, somewhere between about 8,000 and 20,000 years, but much, much longer by any estimate, even the most conservative one, of the 4,000 to 5,000 year range that we used to think based on the oxygen isotope record. So interglacials can be long, and the last interglacial was quite long, and we're nowhere near going to its duration yet in the present interglacial. Well, if it was long, was it warm also? Well, as it turns out, the answer to that is yes. And we'll go back to Hawaii here. Here's an example using this critter. This is Lambus chiagra. I'm sure I'm mispronouncing that, but this is a conch-type shell. It currently lives in this shaded area that you see here in the main part of the Indo-Pacific. But during the last interglacial period, it extended northeastward into Hawaii, as you can see here. So we're looking at a migration in a northward direction of hundreds or maybe even 1,000 or more kilometers to the northeast, indicating warmer waters in the Pacific at that time. Here's another example. This is Strombus mutabalis. This is another shell that is found in the core Indo-Pacific region, but also extends westward into the Indian Ocean and actually occurs all the way up into the Red Sea and along the East African coast, but does not live in Hawaii at the present time. But as you can see, during the last interglacial, it also migrated to the northeast and extended its range. There are a good 8 or 10 species like this that migrated to the north up towards Hawaii during the last interglacial period that do not live there at the present time. It's too cold for them now. The waters were warmer, and we can see that extension of ranges as an indication of warmer waters in Hawaii. Same thing happened on the west coast of North America. We see range extensions of a lot of critters that currently all live only to the south. For reference, right here is about the location of Channel Islands National Park. And what you see in the shaded area here is the present-day range of this particular critter, which is Mexacanthina lugubris. And we've actually found the northernmost occurrence of that little critter right there in Channel Islands National Park on Anacapa Island, a place called Frenchie's Cove. And we found this critter. It's the northernmost occurrence of this that anyone has ever found, and it's right there in Channel Islands National Park. So you're looking at a range extension there of a few hundred kilometers to the north. And this is in an area where things are fairly cool and things don't migrate that readily. It takes a fairly robust temperature change to bring about major range shifts for a lot of creatures, and yet we had it during the last interglacial period 120,000 years ago. Here's another example, in some ways even more impressive. This is Kione, a common bivalve. Doesn't live any farther north than about here, somewhere around Santa Barbara. We also found that Frenchie's Cove on Anacapa Island in Channel Islands National Park, so again, marks its northernmost extent at the present time. But it extended all the way north up to Tamales Bay, north of San Francisco during the last interglacial. So we're looking at a significant range extension here over hundreds of kilometers during that time period. So we see examples then both from Hawaii and the Pacific, from the west coast of North America, of warmer conditions, and we see this worldwide as well. There are a lot of migrations into the Mediterranean from things that live only in West Africa now, in the tropical zone, in Australia, in a lot of other areas as well. A lot of migrations of critters to points farther north, indicating warmer waters. So a third question then, how high was the last interglacial sea level compared to the present interglacial, and how fast can sea level rise? And here's an example from Florida. As I mentioned, we have to go to tectonically stable areas in order to essentially get accurate high water marks or bathtub rings or dipsticks for high sea levels. We can't do this so easily in California because there is always the tectonic component, or the fact that the landscape is being uplifted. But places like Hawaii and Florida, we can do this sort of thing. And here's an example from Florida. This is Windley Key. It's a quarry that is no longer active as a quarry and is now a state geologic park because there are beautiful displays of the Key Largo limestone, which is a coral reef rock that dates to the last interglacial period. And back here in the background, you can see Florida Bay. We're looking to the west. The top of this coral reef is at about 5.5 meters above sea level. We've measured this very precisely. And the species of corals that we see growing in there require at least 3 meters of water depth. Okay, many of them actually have their most favorable habitats much deeper than that, but conservatively at least 3 meters of water depth that we have to look at here for the particular corals that we see in this assemblage within this coral reef rock, because these are all modern species. They're all extant species now. So some complicated mathematics here. Our paleo-sea level is our present-day elevation measurement, 5.5 meters, plus 3 meters of habitat growth, depth, I should say. So 5.5 plus 3 equals 8.5 meters above present. So what we're looking at then during the last interglacial period is a sea level that would have been up here somewhere, about 3 meters above the present-day land surface, which itself is about 5.5 meters above sea level. So we're looking at an 8 meter or 8.5 meter sea level high stand during the last interglacial period. And we can actually test that in another type of geologic record also in Florida. This is downtown Miami, right below the elevated train tracks that you can see here. And what you're seeing here that was spared in all the construction that's gone on over the years, and fortunately this is now a city park, but you can see exposures here of a rock called the Miami oolite. And it's a limestone, like the Key Largo limestone. But this is, although it's got corals in it and a few shells and so on, it's primarily composed of something called ooids, which are little inorganically precipitated carbonates, but they also have uranium in them, and we can date them as well. Sure enough, these date to the last interglacial period. The top of this ooid shoal is about 7.5 meters above sea level. And in the Bahamas, where these kinds of particles are forming at the present time, they form most in water depths of about 1 meter or so. So if we add 1 meter to the 7.5 meters elevation, again, we're getting some higher level mathematics here. 7.5 plus 1 equals about 8.5 meters above present. And that's a coincidentally very good agreement with the record that we see from the Florida Keys. It does indicate a high sea stand significantly above present during the last interglacial period. So if we're talking about 8.5 meters of additional sea level compared to present, where did that come from? The big Laurentide ice sheet that we saw in the eastern part of North America and the Cordilleran ice sheet that we saw in the western part of North America during the last glacial period would not have been around at all. That would have been similar to the kind of addition that they would have made just to get us to the present sea level. To get an additional 8.5 meters of sea level, we have to look at the sorts of ice caps that we still have and kind of make estimates then as to what might have happened to them during the last interglacial period. Greenland can conceivably account for most of it because it's got a sea level equivalent of about 7 meters. But the cores that have been taken up in the north central part of Greenland right here indicate that there were some parts of Greenland that were still present during the last interglacial. The best estimates from the glaciological modelers is that Greenland probably contributed about 3.5 to 4.5 meters of sea level equivalent by melting, much smaller than it is now, but still around a little bit of it during the last interglacial. All of our small ice caps, like the Vatnajökull on Iceland and other small ice caps like that, can only contribute about a half meter, so we don't get much help that way. So where are we going to get that other 3 to 4 meters or so that we need? Our two best alternatives are either the East Antarctic ice sheet, which can conceivably contribute 52 meters, but is quite stable. The West Antarctic ice sheet can conceivably contribute about 3.3 meters. And so that, shown here with this nice aurora around it on this satellite image, that is our best candidate for probably what contributed to the last interglacial sea level rise. Probably some small amount from small ice caps and valley glaciers, about a chunk or so, a half or a little bit more than a half of Greenland, and probably all of the West Antarctic ice sheet. What that means then is that during a major warm interglacial, like the last interglacial, this is susceptible to melting, and this is susceptible to melting, and all of these are susceptible to melting. And this was under conditions where we did not have anywhere near the CO2 concentrations that we do now. Okay, how fast can that rise? This is a trickier thing to try to answer, but how do we get from this to this? How long does it take? And we have a tougher time answering the question of how do we get rid of all of this, and how fast does that take to bring sea level up higher than present? Best we can do is to try to look at some geologic records to say how fast ice sheets like the Laurentide and the Cordilleran can melt to an interglacial period. This next slide shows you an example of that. Here we're looking at 20,000 years ago when we were right in the last glacial period, going right up to the present here, okay, 0 years. And sea level relative to present is marked by a series of submerged reef terraces off of Barbados, Florida, Puerto Rico, and St. Croix that have been very accurately dated. And these are shallow water corals the elkhorn coral, if you're familiar with that, the Cropera palmata, which is a good paleo-sea level marker or past sea level marker. And you can see that at the close of the last glacial maximum, there were periods of time when we had rather gradual sea level rise, which indicates rather gradual melting of the ice sheets, but then a couple of meltwater pulses. Here's one, and another one right in through here, where sea level could rise 2.5 or even more than 3 meters every 100 years or so. So we're looking at very rapid rises of sea level, things that certainly could be observed within the span of a human lifetime. Now, admittedly, this is only a partial analog because this is looking at more mid-latitude glaciers and their response to a major interglacial, but they're less buffered by being in locations that are not as far north as either Greenland or Antarctica. However, we also have to consider that we're also looking at CO2 concentrations that are way higher now than they were even during the last interglacial period when we know sea level was higher, temperatures were warmer, and the interglacial lasted a long time. Okay, so just to give an example though, if you take a look at that last interglacial sea level rise, how would places like this be impacted? Here's Florida. We gave some examples from the Florida Keys and from Miami. What would Florida have looked like during the last interglacial period? Well, pretty much like that. What you're looking at in white here is an outline of the modern Florida coast, and what you're looking at here in brown is what Florida would have been during the last interglacial period with a sea level that was somewhere between 6 and 8 meters higher than present. Some parts of the Florida Peninsula would have been islands, as you can see here. Many of the major coastal cities of Florida, had they existed then, would have been underwater, and a shoreline that is much farther inland than it is now. And we can actually find the shoreline for that last interglacial right along the southern, eastern, and western margins of Florida and find marine deposits that date to those time periods presently occupying the coastal plain of Florida at present. So this means for national parks if we were looking at a future rise in sea level of anywhere between 6 and 8 meters, there are a lot of national parks that would be affected. Here's just some examples of some of the coastal national parks and coastal national seashores where we have low enough elevations that we would have significant effects with sea level rise on a lot of the coastal parks. In places like California, like this, where we have cliffy coasts, this might take the form of significant sea level rise, bringing about sea cliff retreat, a lot of increases in coastal landslides, cliff undercutting, things like that. Along the Gulf Coast and along the East Coast, we might see the effects of higher sea level with the loss of some barrier islands, creation of vast changes in littoral drift and beach sand budgets and this kind of thing. And in places like Alaska, we would see an increase in the rise of water level within the fjords and all the kinds of changes that those would conceivably bring about with regard to habitat and other kinds of effects. So, can it get any worse than that? Don't mean to be a doomsayer here, but it turns out that the last interglacial may not have actually been the highest sea level of the geologic past. During marine isotope stage 11, remember our odd numbers are for oxygen isotope stages are our interglacials. This is one back around 400,000 or so. And this was a period of time that had a lot of conditions very similar to the present with regard to some of the climate forcings that we now know are important with regard to Earth-Sun geometry. The question is, what was sea level back then? And we can answer this question in a few places. We're working on this in Channel Islands National Park because we think there's a record of this high sea stand in Channel Islands National Park in a marine terrace. We know there's one here. This is on the island of Curaçao in the Caribbean. This is the 125,000-year reef that we're looking at right here. It's up around 12 meters, so it's undergone a few meters of uplift. And it goes all the way back to this cliff, and this coral reef terrace is the 400,000-year-old one. We don't know how old this one is. It's much, much older, but this is in an area of very low uplift rate, kind of like Santa Barbara Island and Channel Islands National Park. So it has been experiencing some uplift, but not very much. But knowing what sea level was at the time this terrace was formed, and knowing what its elevation is now, we can calculate a rate of uplift. And knowing the age of this terrace, we can then back out what the past sea level elevation would have been. This is that 400,000-year reef. It's up around 30 meters. We can calculate then what its paleo-sea level was using the rate of uplift, if we assume that the uplift rate hasn't changed much over time. And that's a big assumption, but it's as reasonable a first step as any. And what we get, using a range of possible uplift rates and elevations of the last interglacial period, a past high sea stand for the 400,000-year high sea stand of perhaps 8 to 10 meters, about the range of the last interglacial, or maybe a little bit higher, or if we really want to go wild with our most liberal estimates, 17 to 20 meters above modern sea level. So that would have been a significant high sea stand, relatively recent geologically speaking, but here you're talking about loss of all of Greenland, all of the West Antarctic ice sheet, and perhaps some of the East Antarctic ice sheet as well. Now, just to illustrate what that might mean, if we take a look at our nation's capital, Washington, D.C. downtown area here, on a USGS topographic map with a National Park Service entity right here in the middle at a slightly higher elevation. If we take one of those estimates, or take, say, somewhere in the middle of those two, not 8 to 10, not 17 to 20, but maybe around 12 or so, what would be inundated during, say, a 12-meter high sea level right in between those estimates? Something like this. And the first time I presented this slide at a USGS workshop, one of the guys who works in our Reston, Virginia office pointed out that in an outcrop that he recently found at a construction site, somewhere right around here, he actually found some marine sediments that he's tentatively dated to 400,000, which seems to indicate that perhaps this actually did happen right here, and is faithfully recording our rough guess here as to what would be inundated. Suffice to say, the effect would be significant. We don't know that this is possible given the present climate conditions. We know it's possible within the Earth system because it has happened in the past. And we know that at least 2 other interglacials had sea levels higher than present, the 200,000-year high sea stand and the 120,000-year high sea stand as well. So we know it can happen. It has happened. And we know that the CO2 concentrations in the atmosphere were nowhere near what they are right now during any of those high sea stands. So this is why we need to take a look at some of these periods in the past when sea level was higher and get some sense of what is possible on a lot of the nation's coastlines. And with that, I'll say thank you very much, and I'll take questions. And I've listed my email down here. If questions come up later, please feel free to drop me a line, and with any thoughts or questions you might have, I'll be happy to try to answer them. Thank you very much.
Thank you so much, Dan. That was very interesting. I don't see any questions yet. I just want to remind the audience you can type questions into that question box, and I think both Dan and I will be able to see them if you do so. Right. If no one has a question to get started, I have one question for you, Dan.
Okay.
You know, it always surprises me sometimes, like even on the west coast here of the U.S. or the East Coast too, I'll see different projections of the amount of sea level rise that's predicted for different localities.
Right.
And is the difference solely because of differing uplift rates of those places on the land, or are there other factors that drive that difference?
I think on most, it's a very good question. In fact, it's a really important question. Most of them, I think, are driven by estimates of what degree of warming we might expect based on different scenarios with carbon dioxide. You know, whether we have a diminution of CO2 emissions into the atmosphere, if we more or less stay the same, or with increased fossil fuel use, will we increase CO2 concentrations. That's one of the major drivers for the amount of warming that we might expect, which in turn is going to affect what we see from both thermal expansions of the oceans, which causes a moderate amount of sea level rise, but then also melting of the Greenland and Antarctic ice sheets as well. So it's primarily a function of the conservative versus liberal estimates of the CO2 concentrations in the atmosphere for the most part, I think. So,
okay.
Yeah.
Okay, yeah, we do have a question that came in here from David Enfield, and David asks, how much warmer was it during the last interglacial, and can we answer that for the atmosphere?
It's a good question. We can do a better job with the oceans because we can date those marine deposits or marine fossils more accurately than we can on the land. The best estimates are that it was probably about 2 degrees centigrade or so warmer, perhaps, in a lot of the world's oceans. There was a lot of regional variability. Some places were warmer than others. There was a recent study that came out that indicated that in a lot of parts of the deep sea, out in the centers of the oceans, that things were just only slightly warmer than today. But in a lot of coastal areas, we know it was much warmer than today. But a rough average, maybe a couple of degrees centigrade. On land, it's harder to get the records that we know date specifically to the last interglacial. For those areas where we do have some records, and Alaska is one of them, where we actually see good examples of a migration of the spruce forest boundary to points west in Alaska and points north in Alaska that are presently tundra. And those would also indicate somewhere in the neighborhood of maybe a couple of degrees centigrade or so higher than present. So, but on the continents, much tougher. We just don't have as good a yardstick for a lot of temperature indicators that can be well dated to the last interglacial. And hope that answers your question.
Great. Okay, the questions are coming in. From Lanny and Chad Lockwood. Besides Barnes ice field on Baffin Island, would not the Harding ice field also be a remnant of the Laurentian Cordilleran ice sheet?
I'd have to be refreshed on where that is. The Harding is, don't remember where the Harding is.
Kenai Peninsula, Alaska. It's just south of Anchorage.
Okay.
Kenai Fjords National Park.
Yeah, probably not of the Cordilleran system, but certainly would have been part of some of the smaller ice caps in southern Alaska. So in general, the answer yes, not specifically Laurentide or the Cordilleran, but yes to smaller ice caps there. There's another one that is part of the Laurentide ice sheet in Canada, and that's the Penny ice cap as well. It's a smaller one, but it was too small to show on that map.
Okay. From Ann Whitmore Painter, is it possible to tell how much of the rising ocean was from warmer water temperatures and how much from additions of melted ice?
Yes. There's a lot of oceanographers who are very good at estimating what the amount of thermal expansion would have been that could have caused some sea level rise. And certainly that is a factor. But the majority of that would have been from melting from large ice sheets, not from thermal expansion.
Okay. That is all that I have for questions that are showing up. Does anyone have any last minute question that they want to put in here? If not, Dan, thank you so much.
Thank you. I enjoyed it.
Very interesting presentation, and I can just say to everyone out there, Dan did put up his email address, and as I said, I've worked with Dan for years. He's been extremely gracious with his time, and I'm sure if any of you have follow-up questions or just would like to chat with him, Dan always seems very open to that. So thanks for that involvement that you've had with the National Parks, Dan.
Been my pleasure.
Thanks for doing this presentation.
My pleasure. Thanks so much for organizing. Thanks, everyone.
Bye-bye.
Bye-bye.